Hello everyone, this is Dropping Yang, a second-year PhD student from Professor Pei Zhou's group at the University of Pittsburgh. Today I'm going to present our work in accelerating arbitrary-precision integer multiplication on heterogeneous reconfigurable computing platform, Versal ACAP. This is a joint work from the University of Pittsburgh and the University of Maryland. Our work is open source. You can find it using the GitHub link or scanning the QR code. Arbitrary-precision integer multiplication is widely applied in security, simulation, informatics, and etc. Although primitive data types in programming such as integer or floating point are suitable for most common applications, they cannot be applied to these kind of applications directly. For these types of applications, people can use well-developed libraries such as GMP on CPUs and CGBN on GPUs. Also, people can use many hardware accelerators based on FPGA. FPGA accelerators are promised to provide both good energy efficiency and flexibility. However, in our profiling results, we compare the SOTA FPGA accelerator based in price on U250 with two generations of CPUs and GPUs. We find that the FPGA accelerator is the most inefficient platform in large integer multiplication, which motivates this work. In this work, we identify the inefficiency source of FPGA and propose aim to improve its efficiency. After applying our work to the latest FPGA platform, we bring FPGA back to the most energy-efficient platform among CPU and GPU. To achieve such energy efficiency gain, we first need to know why CPU or GPU is energy efficient. Let's first take a closer look at the algorithm that enables large integer multiplication. Suppose A and B are two large values and cannot multiply them directly using existing hardware. So we first split A and B into smaller pieces evenly and make sure the smaller pieces can utilize the existing hardware. Then we pick up one piece of A and multiply it with all the smaller pieces of B. We do similar multiplications for the rest of A pieces. After the multiplications are finished, we add those multiplication results with the same shift together and propagate the carry from the lowest bit to the highest bit. Finally, we get the multiplication result of A and B. This decomposition method is called the schoolbook method. It has the largest complexity compared with other decomposition methods, such as Karlsruhe or Tom Cook, but it requires less storage for temporary products and has simpler data control logic. Therefore, the schoolbook method is used as a building block in many libraries such as GMP. Now we can go back to the profiling analysis and discuss why FPGA is not energy efficient. The CPU is featured with AVX 512 instructions. The AVX 512 instructions are 512-bit vector instructions on the Intel processors. We use the Intel software development emulator and the Intel VTune profiler to get the instruction breakdown of a 4K multiplier on the CPU. We found that about 78% of instructions are AVX 512 instruction integer fused multiply add. This indicates that the multiplication part can be done very efficiently on the CPU, not to mention that the GPUs are even better at such vector processing. However, the FPGA are typically composed of LUTs, DSPs, DRAM, and URAM. Among them, we can use LUTs and DSPs to do the computation, but neither of them is designed for vector processing. To understand why vector instructions can bring energy efficiency gain, we can go back to the algorithm part. The large integer multiplication is a combination of two distinct processes. The first part is a multiplication part, which has massive independent sub-multiplications. These kind of tasks are byte-level processing and can utilize vector instructions very efficiently. Another part is the carry propagation process, which is a non-sequential process, and is also bit-level processing. The first part is suitable for vector processing, and FPGAs are only good for the second part. So our questions arise. First, can FPGA take advantage of vector processing? For example, let the vector processors to do the multiplication part, and the FPGA to do the carry propagation. Second, will such a heterogeneous system bring any gains in performance or energy efficiency? Lastly, how to find a good mapping strategy and how to make it easy to use. We use Versal ACAP to verify our ideas. Versal ACAP is a newly released 7nm heterogeneous compute platform from AMD. It has an AI engine array that is composed of 400 AI engines, or AE. It also has traditional programmable logic, or FPGA. Lastly, there is an ARM CPU core to run the host programs. Each AE has a high-performance 7-way very long instruction word supported processor and 32 kilobytes local memory. The ARM CPU core and the FPGA can talk to each other through the network on chip, and they are also connected to the DDR. The AE array can communicate with other components through 39 interface I/O tiles with up to 1.2 terabytes per second bandwidth. The AEs are connected to the I/O tiles using the AXI string and the switch boxes. Between the adjacent AEs, they can communicate with each other through the shared memory. Besides, there is a unidirectional high-speed cascade string that connects adjacent AE within the same row. To efficiently leverage both vector processing parallelism and bit-level parallelism, we propose AIM architecture to map arbitrary integer multiplication applications onto the AMD Versal ACAP architecture. AIM architecture utilizes vector processors, or AEs, to compute the submultiplications very efficiently, and use the FPGA to do the carry propagation part. AIM supports two mapping strategies. In the first one, we first group the submultiplications and offload them onto different AEs. In this case, AE 0, 1, and 2 share the same pieces of A. Therefore, the A pieces will be broadcast to these three AE using the same PIO. AE 3, 4, and 5 will share another PIO. Similarly, AEs that use the same pieces of B will share the same PIO. To reduce the data movement between the AE array and the FPGA, we accumulate those partial results that have the same shift in the AE array. For example, AE1 will send its result to the AE3, and AE2 will send its result to the AE4. The partial results will be transferred via the high-speed cascade string. Then, after all computation is finished, AE 0, 3, 4, and 5 will send their results to the FPGA part. On the FPGA side, we design sender modules to load and send data to the AE array. In addition, since AEs cannot directly process the raw data in this case, the sender modules need to rearrange the raw data to use the existing instructions on the AE. In the receiver part, we first use 4 adders to process partial results from each AE in parallel. And then we use another adder to do the final carry propagation process. And then stream the result to the DDR. In this case, we split one task and offload them onto different AIEs. This kind of parallelism is called intra-task parallelism. It requires fewer hardware resources on the IPG side and can use a large number of AIEs. However, the single AIE kernel efficiency is relatively low, especially when the workload is small. In the other mapping strategy, we offload one whole task onto the same AIE, and different AIEs will compute different tasks. To reduce the number of required PIOs, we let multiple AIEs share one PIO in a time multiplexing way. Before sending the data, the PIO senders will attach a header to specify the destination of the input data, and then the AIEs can receive their data in sequential. Similarly, these AIEs will share the same output PIO, but the output order is unknown. Therefore, on the PL side, we first do the carrier propagation part, and then use a reorder buffer to get the correct order, and stream the correct order to the DDR. In this case, different AIEs will compute different tasks simultaneously, and this kind of parallelism is called inter-task parallelism. It typically has a high AIE kernel efficiency, but it requires more hardware resources such as on-chip RAM or PLL, and with a certain hardware resources constraint, only a small number of AIEs can be used. In AIM, we will explore intra-task parallelism and inter-task parallelism to find the optimal configuration. Different workload partition methods will result in different parallelism and thus different performance. And here we show three representative workload partitions. Workload 1 will attempt to maximize the intra-task parallelism. Each AIE will be assigned with subtasks in a whole task. Workload 3 will try to maximize the inter-task parallelism, and we can process different tasks simultaneously. Workload 2 is a combination of workload 1 and workload 3. It will try to find a balanced point between inter-task and intra-task parallelism. We apply these three partition methods to the 8K multiplier. The table shows the maximum implementable designs for these three workloads. Workload 1 uses 306 AIEs, but only achieves 1.6 million tasks per second due to the low AIE kernel efficiency. Workload 3 has the highest AIE kernel efficiency, but only 80 AIE are used under certain hardware resource constraints. Workload 2 is the most performant one, as it finds a balanced point between the intra-task parallelism and inter-task parallelism. In workload 2, we achieve 9.6 million tasks per second using 210 AIEs. Now, let me briefly introduce the implementation of AIM. Each AIE computes a tile of multiplication in a zigzag order. The result of the multiplications within the same column will be accumulated into the same register to save the on-chip storage. As the AIE is a 7-way very long instruction word supported processor, we need to carefully pack load, store, and compute instructions. Besides, we also use double register technique to avoid store. In this way, we can achieve the highest performance in the single AIE kernel. Then we can scale up to the AIE array. First, AIE 0 and 1 can start simultaneously as they do not have any data dependencies. For AIEs within the same row, For AEs within the same column, the upper AE will start first. After it finishes the first column of multiplications, it will transfer the partial results to the following AE. And then they can compute simultaneously on multiplications with different shifts, and the data dependencies are resolved in a fine-grained pipeline. Since the dependent AEs use the high-speed cascade stream to transfer the partial results, they must be physically placed in the same row in the AE array. If we let the compiler to do the placement, the AEs will be placed in a chaotic manner, which will cause routing failures when we use more AEs. To deal with this issue, AIM automatically rearranges the AEs with the consideration of AE array's physical layout, then place them in order. In this way, AIM successfully utilizes up to 396 AEs. In AIM, PL modules and the AE array are all designed in a fine-grained pipeline to achieve the best system-level performance. Besides, the advantage of this pipeline fashion is that users can also integrate their own application logic to the pipeline to achieve the highest performance as long as we keep feed data into the system. Manually tuning the AE and PL kernels is not trivial. To enable fast development, we provide the AIM framework. Users just need to set the multiplication size, hardware constraints to the AIM framework, and a one-time HIS profiling to get the hardware resource consumption and PL modules execution time. For users who use AMD Versal ACAP can omit this HIS profiling step. Then the AIM DSE will find an optimal configuration based on user input and launch the AIM code generator to generate all code needed for AE and PL. Besides, finally, it will use a backend compiler to generate the host executable binary and FPGA configuration bitstream. Now let me show two more complicated applications using AIM. The first one is RSA, an asymmetric cryptographic algorithm. We adopt Montgomery multiplications for fast modular calculation, as shown in this solo code. Only a small portion of code requires multiplications, which can directly use the optimized kernels in AIM. For the rest control logic or non-multiplication computations, we can design separate PL modules and integrate them into the pipeline. This figure shows the timeline of the AIEs and the PL modules. Module 2 and 4 are designed for Montgomery multiplication on FPGA. Module 1 and 5 are the RSA control logic on the FPGA. Module 3 represents the AE kernels. All modules are in a fine-grained pipeline, so as long as we keep feed data into the system, the AE will not be idle. Therefore, we can also achieve very high performance in end-to-end applications. Another application is plotting the Mandelbrot set. The Mandelbrot set is a type of fractal that has detailed structures at arbitrary precision levels. Mandelbrot set can be plotted by performing the divergence test for each sampled points on the complex plane. Specifically, we iteratively calculate FC, where FC is described using the formula, and C is a point on the complex plane. The value of each pixel is the iteration time of the divergence test. Performing the divergence test efficiently is difficult, as every point may require different numbers of multiplications, and we must develop a runtime scheduler. Besides, the Mandelbrot set requires significant precision because it can be magnified infinitely in theory, like this. However, if you use a low precision data type, you will quickly get a blurry image when you zoom in. To further plot detailed structures, you have to increase the precision. Next is our experiment setup. We use VETIS 2021 to compare all designs and verify them on the AMD Versal VCK180 board. For all designs, AIEs are running at 1 GHz and PL is running at the maximum achievable frequency. We select 3 representative applications, such as initial modifications, RSA, and plotting the mandible set to demonstrate the effectiveness of AIM. We compare AIM with the Intel Xeon Gold 6346 CPU and the NVIDIA A5000 GPU, as they are all manufactured in the same generation of technology. Besides, we use well-developed libraries, for instance, GMP on CPU and CGBN on the GPU. We first verify the model accuracy. We let the AIM framework generate several different configurations and predict the performance for the 64K bit multiplication. Then we compile these designs and measure the onboard performance. The results show that our model is very accurate, and the average error is only 1.8%. This indicates that the AIM can find the optimal configuration quickly and accurately. Next, we compare AIM with Intel Xeon 6346 CPU and NVIDIA A5000 GPU. We use AIM to find the optimal configurations for multiplications range from 4K to 256K. The results show that we achieve up to 12x energy efficiency gain over the CPU and 2x energy efficiency gain over GPU. Besides, to be noted, AIM supports much larger multiplications than CGBN on the GPU. We also compare AIM with CPU and GPU in the end-to-end applications. For RSA, we compare AIM with CPU only, since CGBN do not have an RSA implementation. AIM achieve much higher energy efficiency gain over CGBN on CPU. The reason is that the GMP's modular arithmetic is slow. In plotting the mandible set, we use GMP and CGBN on CPU and GPU respectively to plot the same area with AIM, and also achieve higher energy efficiency gain over CPU and GPU. Thanks for listening. If you have any questions, please feel free to connect me via email or submit issues in our GitHub repo. This project is supported by Pitt New Faculty's Startup Fund, the Laboratory for Physical Science, National Science Foundation, and AMD software and hardware donations.